talk about this theorem about infinite sets and how to show infinities have the same size. I'm really proud of the proof with lots of color coding, so stay till the end of the video. When we talk about two things having the same size or cardinality, what we mean is there's a one-to-one correspondence between all the elements in one set and all the elements in the other set. And if your sets are very unwieldy, it might be hard to write this down, and that's where this theorem comes into play. It says if you can illustrate that the set B is so big that it can contain all of A, but then A is so big that it can contain all of B, if both of those are true, then actually those two sets have to have the same size. What we have are two sets, and we have two injective functions. This basically means that A can be made to sit entirely inside of B, and we have the vice versa. Now what we're going to do is we're going to take A and we're going to apply this function, and we get some subset over here, and it's probably not going to be all of B. Because if it were, then this map would actually be one-to-one and onto, and we would have the bijection, that one-to-one correspondence we are after. Similarly, we could start with the set B and we could apply the function g to it, and we get some elements over here inside of A that are going to be like the image of G. And we can do it again. We can take this set here, well, I'm calling A1, and we can map it over here, and I'll call this B2. And if we continue this process, we get a whole chain of subsets on either side. And now let's look at the color coding. So this map here from A to B was one-to-one. And so whatever A is, well, it's going to have the same size as its image over here. And whatever this is, it's going to have the same size as its image over here. Basically, every other set is going to have the same cardinality. So you can see we kind of have this even-odd thing going on with the red sets and the blue sets. Now notice if any of these happen to be equal, then we would have a red set of the same size as a blue set, and that would finish our proof because we're just trying to show that A and B have the same size. Now what we're going to do is we're going to draw a picture of this over here on the left. So the big set A is down here, and then inside of it is this smaller set A1, and inside of that is a smaller set A2. And at the very core of all of this, there might be some stuff that's inside all of them. I tried to make that as a little pink circle down there, and I've kind of written that over there. But just think about this picture. What I'm going to do is I'm going to break up the big red set A as a union of all of these donut-shaped regions. So what I'm doing is I'm peeling off all the layers of A. So A first, as I can think of it, is everything in this outer layer. I've put that here. And then I go one layer deeper, and then another layer deeper. And at the very, very end, I might have to add in this stuff in D. But these are all disjoint sets, right? There's nothing that can be in A1, but not in A2, and then also in A2. And I can do the same thing if I just start with the next layer. If I start with A1, then A1 can be written as this disjoint union of sets as well. Now you've noticed some new color coding. I'm sorry I couldn't get it all in this picture as well. But notice that the yellow sets are going to be all of the same size because remember A has the same size as A2, let's look up here, and then A1 has the same size as A3, and so when we're subtracting them, everything's going to be okay. Specifically, if you think back to that zigzag diagram that we had, those zigzag arrows are actually going to be a bijection between the two orange sets I just talked about. And so now you might notice something, right? We have a red set on top and then a blue set on the bottom, but we can see that they're basically made out of stuff of the same size. In particular, if you wanted to write down a bijection between this top line and the bottom line, we'll just send orange to orange, etc. And then send green to green. You have to go the other way. And then at the very end, you would just send D to itself. So that shows that the two lines at the bottom have to have a bijection between them. I just described one. And therefore, the red set and the blue set have to have the same size. I love this proof because it's like there's lots of creativity, there's lots of pictures, I love colors. Also, even though these sets may be gigantic and completely uncountable, we still get kind of a counting argument at the bottom, and the even and odd numbers come into play because we have alternating every other turn. I'm not a set theorist, so there might be other proofs, but this is the one I learned when I was a student, and I just wanted to share with you. If you like proofs and learning more about math, please consider following or posting a comment and let me know what you'd like me to post about. I'm happy to share math with everybody.